Hello, I'm Wentai from Shanghai Jiao Tong University. Today I will talk about how to recover stateful system components in microkernel. In a monolithic kernel such as Linux, almost all of the kernel subsystems are running in the kernel space without isolation with each other, and the applications are deployed in the user space. While in a microkernel, most of the kernel subsystems are moved to the user space as standalone processes, such as network stack, file system, and device drivers. Only the core components are still running in the kernel space. We name the services that are deployed in the user space as system servers in this talk. In monolithic kernel, applications can use system calls to directly request services from kernel. However, in microkernel, applications rely on the inter-process communication to switch to system servers to access OS services. Since system servers in microkernel are deployed in different processes, which are isolated with each other, and the IPC interfaces exposed by system servers are also limited. A fault in a system server is difficult to propagate to other system servers, applications, and the underlying microkernel, so that microkernel provides better fault isolation than monolithic kernel. But fault isolation is not enough. To ensure that the system servers can provide seamless services to applications, the servers must be recovered from the faults. A naive solution is just to simply restart the system servers to a fresh state, but such solution abandons all the runtime states. We need a fault recovery mechanism that can recover the internal states of the system servers. The system server can encounter various kinds of faults. In our fault model, we aim at the transient faults, which occupies a substantial proportion in the real-world software. This kind of faults is randomly generated by hardware errors, such as bit flip in register or software bugs. For example, a concurrent execution sequence can generate a specific bug. These kind of faults can be rectified by just re-execution. To recover a stateful system server, we propose transaction IPC. The basic idea is that since the system server in microkernel only executes after receiving IPCs from clients, a fault in system server can be considered as a consequence of the IPC. To recover the faults, we can abort the current executing IPC by rolling back the system server states to the states before the IPC's execution, which is the consistent state. Apart from recoverability, transaction IPC also aims at providing good compatibility by introducing only minor human effort to make an existing system server recoverable. The performance degradation incurred by transaction IPC should also not be substantial. We abort the current executing IPC by rolling back all the memory modified by it. The first method we use to roll back the memory is a transparent solution, which is called instruction level undo lock. We instrument all the write instructions, and before every write instruction, we record the old value of the address that will soon be updated. Once the error occurs, we can reset the value to the old value before the IPC's execution. But since there are so many write instructions in the software, the excessive instrument incurs non-negligible runtime overhead. But we observe that in system server, there are some hot memory regions that are highly possible to be updated during IPC's execution. Slapshot is more suitable to roll back the memories in the hot regions. Instead of using instruction level undo lock, we generate snapshots for these hot regions in advance of the IPC's execution so that the overhead of the runtime instrument is avoided. But there's still a question that how can we know that which memory regions should adopt a snapshot? To answer the question, we need to study how memory states in system servers are maintained. We find that the memory states in system servers are naturally partitioned by IPC. For example, if a network stack server provides socket abstraction, the IPC operations to a socket is likely to update the data in the socket itself, but it will not touch other unrelated sockets. We define such phenomena as the IPC session to describe that the IPC is likely to update only part of memory in the system server. There are also some global states that can be updated by all the IPC clients. An IPC with specific session may also update data in another session. Still take socket as example. If two sockets establish connection with each other, The IPC operation to a socket may update data in another socket. Our snapshot mechanism is guided by the IPC session. Since different IPC sessions have different hot regions, the potential hot regions can be arbitrarily large when the number of clients increases. So, instead of generating snapshots for the whole system server, we only take snapshots for sessions that are possible to be updated in the current IPC. But we still faces two challenges. The first is how to identify a state belong to a global state or the per IPC session state. Another question is how to manage the cross-session updates. To solve the first challenge, we provide an offline profiling tool to gather the memory addresses updated by each IPC session. It analyzes from two dimensions. The first is whether the memory region is frequently updated, and the second is whether the region is updated by most IPC sessions. If both of the two conditions holds, the states belongs to the IPC session states. If only the first condition holds, it belongs to the global states. With the help of the profiling tool, programmers should manually mark the states with the annotations. To solve the second challenge, we introduce an intra-process isolation mechanism. It isolates part of memory in a process. When accessing the memory, an exception will occur. At the initialization, an IPC can only update the data in its own session. In the demo below, the IPC can only update data in session A, and the session A snapshot is generated. When you update data in session B, an exception will occur since it is prohibited by intra-process isolation. We then grant permission to access data in session B. So the future IPC can now update data in both IPC sessions, and a snapshot for both of the sessions are generated. We provide runtime to manage undo log and snapshot. Before the IPC's execution, the runtime ensures that the related snapshots are generated. Then the IPC starts the execution, and the runtime maintains undo log. After IPC finishes, the runtime generates new snapshots and deletes the undo log. There are some other designs discussed in the paper, including how can we handle concurrent IPC and blocking IPC. We port transaction IPC to LWIP level stack and x86 file system, both with less than 100 lines of code modified. The fault injection test shows that the system servers can recover from 98% of the errors. For the performance, transaction IPC incurs an overhead at about 25% in Apache HTTP benchmark with a single thread, which dramatically outperforms existing solutions. In summary, transaction IPC adopts a hybrid method of instruction-level undo log and snapshot mechanisms, which is guided by IPC's semantic. It can efficiently recover stateful system servers in microkernel. Thanks for listening.